In this video, we're going to talk about least squares for the simple linear regression model. So developing our how we arrive at our least squares estimators. And we've already done this, but now we're going to use matrices to show basically the same results that we showed prior without matrices. All right. So remember what our simple linear regression model, we have yi equals beta naught, which is our intercept, times beta 1, which is our slope, times x sub I, plus epsilon sub I for I equals 1 to n, right? And if we use matrices to represent this model, we have a vector of y's equals x times beta plus epsilon, okay? So y, this y here, is an n times 1 vector. X is our design matrix, and it is n times 2. Beta is our model parameters, beta 0 and beta 1. It's a vector, and it is 2 by 1. And lastly, epsilon is a vector that is n by 1, all the model error terms. Okay, so beta, our model parameters, we have beta 0 and beta 1. Right? What we want is we want to figure out how to estimate beta, right? So our estimate of beta for right now, we're going to call this B, right? And B is B0 and B1. Okay, so this is what we want to know. How do we estimate B, right? And we're going to use least squares to get to it, right? So this is our observed y vector, right? These are all the y's that we observe, right? But if we have b, then we can also have the predicted values of y, which is y hat, which is going to equal x times b, right? Our design matrix times these estimates of beta, okay? So our residuals are e, which is y minus y hat, right? And remember, these are vectors now. So e is an n by 1 vector, y is an n by 1 vector, and y hat is also an n by 1 vector. Okay, so we could also write this error term. Well, let me go ahead and write this. This is the residuals. So these are our model residuals. Okay, and we can also write this as e equals y minus x times b, right? Because y hat is x times b. All right, so the idea in least squares is to minimize the sum of squared residuals, right? So our goal when we're doing least squares development, we want to minimize the sum, right, from I equals 1 to n of e sub I squared, right? So that's the way we've written it prior, before we had matrix notation. Now that we have matrix notation, this is the same thing as saying that we want to minimize E transpose times E, right? So E transpose would be 1 times n, right? Its dimension is 1 times n. E is n times 1. So when you multiply these together, you get a 1 by 1, which is basically just a scalar, which is it's the sum of these squared error terms, right? So in other words, we can plug in what is E. So basically we want to minimize y minus xb transpose times y minus xb. All right, so that's our goal. All right, so how do we find the minimum of this term here, of these terms? How do we find the minimum of this? Well, we take the derivative and set it equal to 0. So let's do that. So what we want to do is we want to take the derivative with regards to the vector b of y minus xb prime times y minus xb, and we want to set it equal to 0. Okay. So to do this, let's go ahead and put this transpose into our parentheses. Okay, so I'm going to leave this out front, the partial derivative with regards to b, and I'll have, when I put this in, I'm going to have y prime minus b prime times x prime. Okay, remember when you transpose a product, you have to reverse the order of that product. Okay, times y minus xb. Okay, so now let's go ahead and distribute these parentheses. So first thing I'll do is I'll multiply y times y. Okay, let me scroll down. All right, so I'll have y transpose times y. Okay, then I'll have y transpose times, so that's positive and negative, so that makes minus y transpose times xb, right? And then I'll have this b transpose x transpose times y, so that's negative b transpose x transpose times y, and then b transpose x transpose times, so it's positive b transpose x transpose times xb, okay, equals 0. Make sure I should have 4 terms. 1, 2, 3, 4. Good. Okay. So multiply each piece of this difference by each piece of that difference. Right? And notice that, let's look here at the dimensions of this guy. So y transpose is 1 times n. X is n times 2. And b is 2 times 1. Right? So when you multiply these out, right, so the n's cancel, the 2's cancel, and you're left with a 1 by 1, which is a scalar. Good. Each piece of these should all be scalars. Okay? And so you see that this is the same as this, right? Because when you multiply them out, they're scalars. So these guys are exactly the same. So let me go ahead and combine them in this next step. So I have the partial derivative with regards to b, y prime y minus 2 b transpose x transpose y plus b transpose x transpose xb. Right, so that's 0. Okay, so I've simplified basically. That's all I've done. Now I'm ready to go ahead and take this partial derivative. All right, now the partial derivative of y, right, there's no b here. So for this first piece here, we're going to have, basically, it's nothing, 0, okay? Then the second piece, it only has one b. So when you take the derivative of it, it's going to be 2, and then the b just basically drops away, times x prime y. And then plus, now there's 2 b's. Okay, you can think of that as like, it's kind of like a b squared. So the b or this 2 gets dropped down, and you're left with x prime x times b. Okay, and set that equals 0. Okay, so now all I have to do is solve for b, right? And I can add 2x prime y to both sides. So equals 2x prime y, right? Divide both sides by 2, so the 2's go away. And then lastly, to get rid of this, you can't just divide by a matrix, right? This is, remember, these x's are matrices. So what we do instead is we multiply both sides by the inverse of that. So we'll have x prime x inverse times x prime x equals, right, and if you did that in the front, you have to do it on the front on the other side as well, x prime x inverse times x prime y, right? And now the inverse and the non-inverse version, they cancel each other. That basically becomes like an index matrix, and you're left with just b. Okay, so let me see, I think I ran out of space on the bottom here, so let me go ahead and just write this up here. So I'm left with b equals x prime x inverse x prime y. Okay, and a lot of times you'll see that written with parentheses around x prime y. All right, so there you have it. This B is our least squares estimator of beta, right, in matrix notation. And let's just double check that we have the right dimensions. So remember, B is 2 by 1. X is n by 2. So X transpose would be 2 by n. X is n by 2. Right? And when you take the inverse, that's the inverse of a 2 by 2, which will also be a 2 by 2. Then we have x prime again, so that's going to be a 2 by n. And then y, which is a n by 1. So these guys cancel. And if you continue looking at if we look at our dimensions, the 2's cancel here. And what are you left with? You're left with a 2 by 1, right, after you do all the product. So this 2 by 1 equals a 2 by 1. That works.